Hi, I'm Mike Swanbom, and today I'd like to show you how you can analyze a section that is shaped like an I-beam, how you can analyze that for certain torsional properties. And specifically what we're going to look at is we're going to look at the shearing stress that is induced in the section when it is twisted, as well as the angle of twist that it undergoes, and then finally we'll look at a torsional spring rate. The specific problem that I'd like to do this for is this unequal flanged I-beam that I have. There's a table full of different kinds of them here, and so we look up here to figure out the exact one that we'll be looking at. It's a 300 ASB 155 I-beam, and so let me go ahead and kind of pick that one out of the table down here. It's this one right here. Okay, and because a lot of those parameters are very meaningful to us, let's go ahead and populate this figure over here with the various variables that we care about. We'll start with this D, that's the overall depth of the section. That's going to be 326 millimeters. Another thing that matters to us are the thickness of the flanges. That's these T values right here, top and bottom flanges. It says here that those have a thickness of 32 millimeters for this section. Okay. The other thing, one of the other things that we're going to need is the thickness of the web portion. That's this portion right here. And so the thickness there of that web portion is going to be 16 millimeters. Okay, and then lastly what we want are the widths of the top and bottom flanges. So we have 179 millimeters, and down here we have 289 millimeters. And that should just about cover all of the different dimensions that we want. So since I won't need the other tabular data here, let me go ahead and grab a little screenshot of the information that we do want to make sure that we have here, and I'm going to drop that onto my page right here. Okay. Now, let's look through the rest of this problem. We've figured out what cross-section we're actually dealing with. It's going to be composed of 1018 hot-rolled steel. Let me go ahead and put the information that's critical on that. What we want to know is we want to know the, first of all, modulus of rigidity. Okay. That modulus of rigidity, G, for this material, this, for all steels in the table in the back of the Shigley book, it says that for carbon steels we have 79.3 gigapascals. This is for carbon steel, and that is in table A5. Okay, so that's one piece of information we can use right there. Also, 1018 hot rolled steel, we can look in table A20, and table A20 will tell us that the yielding strength for this material is going to be 220 megapascals. Okay, so those are some material properties that we are going to need for this. We'll use them here in just a minute, so I've kind of used that piece of information. We're next going to look at, okay, we need a factor of safety of 1.5 against yielding. We'll use that in just a second. We're supposed to basically be finding a torque that this section can carry without yielding, and then we want to have this factor of safety of 1.5. Okay, and then for an 8-meter long segment, we want to figure out this angle of twist and a torsional spring rate. The book doesn't have equations listed in the normal part of the book, kind of in the text of the book, but it does actually have some interesting information on exercise, and I'll write this down. Exercise 352. Exercise 352 has these equations. First of all, the angle of twist per unit length is going to be equal to 3 t sub I over G L sub I C cubed. Okay. The next, so let me actually talk through this real quick. This is saying that if you know the angle of twist per unit length for a section, that you can actually look at the amount of torque carried in that segment of the cross-section. That's what the T sub I means. In other words, if you take a cross-section like this, you can divide it up into a few different parts, and you can look at how much torque each part contributes. Actually, let me go ahead and do that real quick. On this particular one, we basically draw a couple of divisions, and we are going to look at this middle part. This is basically the web. That's going to be one of our segments, and then up here is one of our flanges. That's another segment we'll look at, and down here we'll look at the other flange. Okay. And so rather than use numbers, let me just go ahead and label them. This is the web in the middle. Up here, this is the top flange. Down here, this is the bottom flange. What we're saying here is that if we know the angle of twist per unit length, it's going to be related to the individual parts of this. T sub I, that means like just the torque that the web carries. L sub I, that is the length of the median line of just the web. C, and that's actually, I missed it on here, it's supposed to be C sub I. That is the amount of thickness that you have for each segment. And so that's another thing that plays a part there. Okay. Another equation that's given for exercise 353, or excuse me, 352, is that the maximum stress is going to be equal to the modulus of rigidity times the angle of twist per unit length times C max. C max in this case refers to a segment or a cross-section that has multiple segments, and the C max is the maximum thickness that you have in that cross-section. In other words, for this one, we basically have T being one of those thicknesses, 32 millimeters, and lowercase t is another thickness, that one's 16 millimeters. Between those two, the 32 millimeters is larger, and so we would use that in this equation to figure out what our maximum shearing stress is. And the last equation that I want to put on here is that the total amount of torque that a cross-section carries is equal to G times theta sub L over 3 times the sum, and we'll say I equal 1 to n here, basically where n is the number of segments that compose the cross-section, of L sub I and C sub I cubed. Okay. What this is basically saying is, if you imagine this equation up here, you're rewriting that equation, but you're basically summing up all of the different torques that you would need to figure out the overall torque. And the idea here is that each of the segments contributes a certain amount of torque to the overall, the total amount of torque that is carried. And what you're doing here is you're accounting for the contribution of each of those torques. One of the assumptions that we make, and it's relatively true, is that the angle of twist per unit length for these cross sections remains constant for each segment. So the different segments don't have different amounts of twist. They all have the same amount of twist per unit of length. So these are the expressions that we are going to use to solve this problem. All right. How do we use this factor of safety of 1.5? Well, actually our starting point is at this equation right here. This equation right here, since it's predicting, this equation predicts how much shearing stress we've got, what we can do is we can plug in an allowable stress in for that maximum shearing stress, And by doing that, we can calculate the angle of twist per unit length that causes that amount of allowable stress, and that gives us our limit. So let me show you what that looks like here. Okay. What we'll do here is, we want to define yielding as the criteria that is failure for this cross section, and so this strength, this yielding strength that we have right here, is in a normal orientation, and this is where we have to use this assumption that's kind of handed to us in the problem here. Use distortion energy theory to estimate yielding strength in shear. Okay, because we have it in a normal orientation, we want it in shear. So what we'll do there is we'll take that and say the 220 megapascals, which is a strength again in a normal orientation, if you take that and you divide it by the square root of 3, that is what distortion energy theory predicts the yielding strength is going to be in shear if you know what it is in a normal orientation. Okay, so that's kind of our first step, is divide by the square root of 3 in order to get the shearing strength or the shearing strength rather than the normal strength. All right. But the other thing that we will do here is we don't want to take the stress level right up to that amount that would cause it to shear or to yield in shear. What we want to do instead is back off a little bit, and that's where we apply our factor of safety. And then what we'll do is we'll equate this, based on this equation up here, we'll equate this to the modulus of rigidity, which for this material is 79.3 gigapascals, okay, multiplied by theta sub L is again the angle of twist per unit length, and then our maximum thickness of any of the segments here is 32 millimeters. That applies actually for both the top and the bottom flange. Okay, and so let me go ahead and actually just rearrange this real quick. This tells me that my angle of twist per unit length is going to be equal to 220 megapascals over square root of 3 times 1.5 times 79.3 gigapascals times 32 millimeters. Okay, now one of the things that we need to do here is think about our units. And one thing to note here is that there is a relationship between megapascals and gigapascals, and the relationship goes by a factor of 1,000. So if I want to put in here a gigapascal, it is 1,000 megapascals. Okay, the other thing that I'll put in here, these millimeters that we have in the denominator, I need to get rid of those in some way. And so in order to get rid of those, I can essentially in the denominator down here multiply by a meter per 1,000 millimeters. You'll notice there this factor of 1,000 actually just exactly cancels itself out, and our angle of twist per unit length is just radians. You see that there's no other units besides just one unit of meters in the denominator. So the way we interpret that is that the number that comes out of here is a number of radians per meter, and the value for that ends up being 0.03336 radians per meter. And if we want to express that in degrees per meter, we can do that as well. It is 1.9117 degrees per meter. Okay, and that's our first step of the process. What we have here is this is the amount of angle of twist per unit length that gives us the amount of shearing stress that we can tolerate in this material while maintaining our factor of safety of 1.5. All right, this is very, very helpful. What we can do next is take this angle of twist and apply it up here into this equation for theta sub L, and we can go back in and calculate at that angle of twist how much torque is each segment contributing to the overall torque. Okay, so that's our next step. All right, so in this next step, what we're going to do here is actually calculate for T sub I. And instead of calling it T sub I, I'm going to say, for the first one that I'll look at, is the torque carried in the web. Okay, and the torque carried in the web is going to be equal to, we're actually really going to use an expression that looks a lot like this, only we don't need the summation because we're just going to do it for each segment one by one. Okay, so the torque carried in the web is just going to be equal to the modulus of rigidity, 79.3 GPa, okay, multiplied by the angle of twist per unit length, okay. The next two parameters we need are the length of the median line of this particular segment. And you'll notice here, based on how I defined that web, it actually stops short of the entire depth D. Okay, so we basically need to take the entire depth D and subtract off 2 times our 32 millimeters. Where's the other one? There it is. 2 times our 32 millimeters in order to get the length of that median line of the web. Okay, so what that looks like is 326 millimeters minus 2 times 32 millimeters. I'm going to give myself just a little bit more room here. Okay, but we're still not quite done. We need one more factor up there in the numerator because what we just dealt with was this length of the median line. The next thing we need to do is to take the thickness value that you see right there that we've called C sub I. That's just the thickness of this portion that we're working on, which is the web, and that's 16 millimeters. Okay. In the denominator, what do we have? Well, we really just have a 3. And I'm just now noticing that I forgot to put my cubed term on my 16 millimeters right here. All right, so what we want to do now is we want to analyze the units on this and make sure that we're in good shape as far as that's concerned. So what I'm going to do is first of all look at the gigapascals and convert that into values that are relative to newtons and meters. Giga is 10 to the 9th. A Pascal is a Newton per square meter. And so if I take 10 to the 9th Newton per square meter and divide by gigapascals, that gives me my conversion that I can use there. The other one that I need to look at are my millimeters here. and we have here millimeters cubed. We also have another factor of millimeters, and so I have 1,000 millimeters are in 1 meter, and I need to take that and put it to the 4th. All right, now we're at a point where if we just enter all of these values into a calculator, what will come out, we'll think about what will come out. GPA cancels. Radians is not even really a unit. We have meters here, and we will turn all of these millimeters into meters. And so what we have there is, meters squared and with another meters in the denominator. Okay, and then we have meters to the 4th in the numerator, so that's meters to the 4th over meters cubed. So that ends up giving us meters along with the newtons, and that makes us feel good that our units for torque come out in Newton meters. So what comes out of this then is 946.59 Newton meters. And that's how much torque is carried in just the web portion of this cross section. All right, we're going to do something similar now for the top flange. Okay, for the top flange, again, we're going to have 79.3 gigapascals times the angle of twist per unit length. In this case, we don't have to do anything special with the length because that top flange is really, the length of it is really just that value of 179 millimeters. And then the thickness of that top flange is 32 millimeters. And that thickness is taken to the 3rd power. Okay. All of this gets divided by 3. All right, again, we apply the same conversions that we did before. 10 to the 9th newtons per square meter. That's a gigapascal. We also have a meter is 1,000 millimeters, and that is taken to the 4th power. And once we put those in there, we can plug all these numbers in, and we get that the torque carried in the top flange, the torque carried in the top flange is just going to be equal to 5,173.7 Newton meters. Okay, so the next step after coming up with that torque that just the top flange is carrying is to try to do the same idea for the bottom flange, and that's not hard. The torque that the bottom flange carries is just going to be equal to, again, 79.3 gigapascals times 0.03336 radians per meter. That's the angle of twist per unit length. The next parameter is the length of just this segment for the bottom flange, and that is going to be 289 millimeters. And then the last parameter there is the thickness of that flange, which is going to be 32 millimeters, and that's taken to the 3rd power. All of this gets divided by 3. We apply the same conversion factors we did a second ago. 10 to the 9th newtons per square meter is a gigapascal, and a meter per 1,000 millimeters is what we do to take care of the millimeters. Okay, so once we plug all of this in, this ends up giving us 8,353.1 Newton meters. Okay, so we figured out what the angle of twist per unit length was that the thing could tolerate before we go beyond that 1.5 factor of safety. We've now come up with how much torque each segment contributes in order to get to that level. And so let's take those torques and add them all together, because that's the overall torque that the whole cross section carries. Okay, so what that looks like is that the total torque is equal to the torque carried in the web plus the torque carried in the upper flange. I think I called that the top flange. And then plus the torque carried in the bottom flange. Okay, and so we'll just add those numbers up. I'm going to have to go back and review these. We had 946.59 Newton meters. We had 5,173.7 Newton meters. And we had 8,353.1 Newton meters. And when we add all of these up, it gives us 14,473.4 Newton meters. And so that answers one of our questions that we had up here. That question that we just answered was, what is this maximum torque that we can apply before reaching or exceeding this 1.5 factor of safety? All right, so we figured that part out. We actually, along the way, figured out what the angle of twist per unit length was. Remember, that was our 0.0336 radians per meter of length. So we've actually done those two parts. Now what we want to do is plug in this information that we're going to apply this torque to an 8-meter long segment of this beam so that we can find the angle of twist and the torsional spring rate. All right, so here's what that looks like. We are going to take, to find our overall angle of twist, theta, we're going to take our angle of twist per unit length and multiply by the length of the beam. Okay, so for us, what that looks like is we have 0.03336 radians per meter multiplied by 8 meters. And this gives us our overall angle of twist, which turns out to be 0.267 radians or if you want to express that in degrees, that turns out to be 15.295 degrees. All right, and we're almost there, because what the last thing we want to do here is to figure out what the torsional spring rate is. Torsional spring rate is not complicated. The torsional spring rate is defined as the amount of torque you apply over the amount of angle of twist that results. So for us, we look at the amount of torque that we apply, which is 14,473.4 Newton meters. And we divide by 0.267 radians. And when we plug those in, that turns out to be 54,216.7 Newton meters per radian. Or if you want to express this in terms of Newton meters per degree, this is just 946.3 Newton meters per degree. Okay. And just as a matter of getting everything on this last screen here, let's remember that our angle of twist per unit length was 0.3336 radians per meter. Okay, and this addresses all of the requested information in this problem. Okay. One last couple of comments here. Those of you who are following along with this calculation, you may have been trying to follow along. Many of these spots I truncated some of the decimal places, and that might mean that if you try to plug in the exact numbers I have in each of my equations that I've listed so far, you may not come up with the exact numbers. I carried all the decimal places through for each step so that I wouldn't accumulate error due to how I chase that through each step. So just take that under advisement. So I'm glad that you watched this. I hope that it was helpful, and if it was, please subscribe to my channel, hit like, and comment below if there's anything else you'd like to know, or just anything that you would like to say about this problem. Thank you for watching.